we're asked to determine the sum of the given radical expressions. In order to add radical expressions, we must have like radicals are radicals in which a radical part is exactly the same, which means like radicals have the same index and the same radicand. However, before we identify the like radicals, we must first simplify each radical completely. So for number 1, we have 2 square root 18 plus square root 50. The first step is to simplify the square root of 18 and the square root of 50. To do this, we need to identify any perfect square factors of 18 and 50. We will do this by looking at the prime factorization of 18 and 50. So this is equal to 2 times the square root of, the prime factorization of 18 is 2 times 3 times 3. Notice how this shows 18 contains the perfect square factor of 3 times 3, or 3 squared. And then we have plus the square root of the prime factorization of 50 is 2 times 5 times 5. Notice this shows us that 50 contains the perfect square factor of 5 times 5, or 5 squared. Let's write this one more time using exponents before we simplify the square roots. This is equal to 2 times the square root of 2 times 3 squared plus the square root of 2 times 5 squared. And now we'll simplify the square roots. The square root of 3 squared simplifies to 1 factor of 3. And because we already have a 2 here, we multiply the 2 and the 3. 2 times 3 is equal to 6. This simplifies to 6 square root 2 plus the square root of 5 squared simplifies to 1 factor of 5. This simplifies to plus 5 square root 2. Now that we've simplified both square roots, notice how we do have like radicals because both terms contain the square root of 2. Or more formally, these are like radicals because both have an index of 2 and a radicand of 2. And we add like radicals, just like we add like terms, treating the radical, or in this case the square root, as if it was a variable. So 6 square root 2 plus 5 square root 2 equals 11 square root 2. We added the 6 and the 5 to get 11, and the square root 2 remained the same. For number 2, we have x times the cube root of x squared y to the 5th plus y times the cube root of x to the 5th y squared. The first step is to simplify both cube roots. Because we have a cube root, or because the index is 3, we're looking for groups of 3 equal factors of the radicand. So for this first radical, we have x times the cube root. X squared does not contain any perfect cube factors, so we have x squared. But y to the 5th does have a perfect cube factor of y to the 3rd. Let's write y to the 5th as y to the 3rd times y squared. And then we have plus y times the cube root of x to the 5th y squared. Because we're looking for perfect cube factors, let's write x to the 5th as x to the 3rd times x squared, and we still have times y squared. Again, because we're looking for perfect cube factors, let's go ahead and circle the perfect cubes under the radicals. So y cubed is a perfect cube, and so is x cubed. And now let's simplify. The cube root of y cubed is equal to 1 factor of y. Because we already have an x here, we multiply the x and the y, which gives us xy times the cube root of x squared y squared plus the cube root of x cubed is equal to 1 factor of x. And because we already have a y here, we multiply the x and the y, giving us xy times the cube root of x squared y squared. Now that we've simplified, notice how we do have 2 like radicals because the radical part is exactly the same, meaning both indexes are equal to 3 and both radicands are x squared y squared. So we can determine the sum. To determine the sum, we add the expressions in front of the cube roots. Xy plus xy is equal to 2xy, and therefore the sum is equal to 2xy times the cube root of x squared y squared. So notice how to determine the sum. we added xy and xy to get 2xy, and the radical part, or the cube root of x squared y squared, remained exactly the same. I hope you found this helpful.